present finite state machine. So these are the topics to discuss. So we have state machines, reactive behavior with state, search and approach, and implementation of FSM or finite state machines. So what are state machines? So a finite state machines, also known as finite state automation, is an abstract device consisting of a set of states, including a start state or sometimes with an end state, an alphabet of symbols that serves as a set of possible inputs to the machine, and a transition function that maps each state to another state or to itself for any given input symbol. So the machine operates by being fed a string of symbols and moves through a series of states according to the transition function. So what is the output? So it depends. So different types of FSM are distinguished depending on if the output is produced and how it is produced before or after a transition. So consider a toaster or an oven toaster. So initially, the toaster is in the off state or power off. So when you push the lever down, so a transition is made to an off state and the heating elements are turned on. So for example, you turn the knob into 3 minutes. So when you push that lever down into 3 minutes, so it changed the state from off, so transition from off to heating elements to turned on. So finally, when the timer expires, a transition is made back to off state and the heating elements are turned off. So this example of a toaster can be discussed or can be displayed using state diagrams. So on this example, so this is the start. So from off state, if you this is what we call the condition, this is the condition and this is the action. So this is the transition. So if you turn the lever down, it will turn the heat on and it will transition from off state to on state. So since you turn the heat on and there's a timer, when the timer expired, so the heating elements will turn off and then from on state it will transition to an off state. So this state is denoted by a circle labeled with the name of the state, so off and on. States are given short names to save space and their full names are given in a box next to the state. So this is off means toaster off and on means toaster on. So a finite state machine consists of a set of states and a set of transitions between pairs of states. So a transition is labeled condition, as I have said earlier, and action. So a condition can cause the transition to be taken and an action that is performed. So action is the performed when the transition is taken. So the incoming arrow, so as you can see on the graph, so the incoming arrow denotes the initial state. I mean this one, so the arrow denotes the initial state. So a transition is shown as an arrow from source state to the target state, same as here. So the action is not continuing. For example, the action means turn left means set the motors so that the robot turns left. So but the transition to the next state is taken without waiting for the robot to reach a specific position. So next topic is the reactive behavior with state. So we have here a specification of a Breitenberg vehicle whose behavior is non-reactive. So the specification is persistent. So the robot moves forwards until it detects an object. It then moves backwards for 1 second and reverse to move forward again. So this is the finite state machine of this Brightenberg vehicle. So initially when the system is turned on, so the motors are set to move forwards. So this one. So this is the start. So when the machine is turned on, it is initially set to forward. So since the specification did not imply if the start is forward or backward, so usually it is always on forward state. So when you turn on a motor, so it is set to forward. So the condition true is always true. So this done unconditionally. So in state forward, if an object is detected, so if we have a condition here, so if it detects an object, so if an object is detected, the transition to state back is taken. So we transition from forward to back states to back state. So the robot moves backwards. So we set the motor backwards and set the timer. Since on the specification, it only moves backward for 1 second. So if there is no timer, if we set motor backwards, it will forever set. If we, the motor will forever run backwards. So we need to set a timer for the motor to stop moving backward. So the motor or the robot moves backward and the timer is set. So when 1 second has passed, the timer expires. So after 1 second, the timer expires, then the transition state from back will go to forwarding state or forward state. Since the timer already expired, remember this is a condition. If the timer expired, you set the motors to forward. So from back state, you go to forward state. So FWD means the robot moving forward, and back meaning the robot moving backwards. So if an object is detected when the robot is in the back state, so no action is performed. Why? Because in our specification, it doesn't specify that the robot will do something, will react on a something, or will do something if the robot encounters an object when he's moving backwards. So our FSM has only ways, or if he only detected a object when the robot is moving forward, but when it's moving backward, so it will do nothing. So no action is performed because there is no transition labeled with this condition. So this shows that the behavior is not reactive. So it's not reactive. So that is, it depends on the current state of the robot as well as the event that occurs. So we have an activity here. It is consistent. So it says that draw the state diagram of a consistent Breitenberg vehicle. So the specification. So the robot cycles through four states, changing state every 1 second, moving forwards, turning left, turning right, and moving backwards. So, so we have here a website where I found that we can create an FSM here. So this is the one that I've created. So this is a very helpful website. So we can just double click and it will create a new state. And if you want to join states, so a very helpful sites site that we can use. So it also has details on how to use the site. So let's get back. So from the activity, so it says that the robot cycles to four states. So meaning uh, from forward, turn left, turn right, and moving backward. So let's say that those are the sequence. So it doesn't say that it will be randomly go to those states. So from forward, left, right, and backwards. So at the start, so the timer starts and we set the motor forward. And every 1 second, so you start the timer. So when the timer expired, this is a condition. So the action, it will turn left and it will set the timer again. So it will turn left, then timer expired. When the timer expired, it will turn right and then reset the timer from right. So when the timer again expired, it will set the motor backwards and then reset, vice versa until it reach forward again and then left. So it will be just like a loop. So FWD means forward, moving backward, left T for turning left, and RGT for turning right. So this is the state diagram for a consistent Breitenberg vehicle. So next is the search and approach. So specification. So for the search and approach, so the robot searches left and right. So it could be positive 45 degrees or negative 45 degrees. And when it detects an object, so the robot approaches the object and stops when it is near the object. So there are two configurations of a sensors of a robot that enable it to search left and right. So if the sensors are fixed to the body of a robot, just like this illustration, so the robot itself has to turn left or right. Otherwise, if the sensor is mounted, so just like this one, this is an ultrasonic sensor that is mounted to the robot. So the sensor is the one who's turning left or right, not the robot itself. So we assume that the robot has fixed sensors. So we will use this kind of illustration. So on this figure, so this shows the state diagram for search and approach. So the robot is initially searching left. So when it is on, it will search left. So it will look at 45 degrees and then turn right. Uh, and when it is on the right, so it can turn left at negative 45 degrees. So as you can see, both left and right can go directly to the approach state. So if when they already detected an object, so it will set the motor forward, so it will approach the object. And when it is near the object, it will set the motor off till it is found. So as you can see, there is a final state labeled, found and denoted by a double circle in this diagram. So a final state machine is finite in the sense that it contains a finite number of states and transitions. So however, its behavior can be finite or infinite. So this figure demonstrates finite behavior because the robot will stop when it has found an object and approach it. But it can also be infinite if there was uh, if an object was never found. So the robot continues indefinitely to search left and right. So persistent Breitenberg vehicle has infinite behavior because it continues to move without stopping. So our first example. So a toaster also demonstrates infinite behavior because it can keep toasting slices of bread forever until you unplug the toaster or you run out of bread. So the second concept, so this one, is a non-determinism. So why it is called non-determinism? Because when you go into a state, so you cannot predict or you cannot determine what is the next state because it depends. So from this state, it can go to right, can turn right or it can approach. So you can never determine. So it is called non-determinism. So states left and right each have two outgoing transitions, one for reaching the edge of the sector being searched and one for detecting an object. So the meaning of non-determinism is that any of the outgoing transitions may be taken. So there are three possibilities here. First, the object is detected, so it goes to approach. So, but the search is not at an edge of the sector. So, meaning uh, it approach an object, but it will not. It approach and then it's. There's no object detected. So in that case, so the transition to approach is taken. So second is the search is at an edge of the sector but an object is not detected. So in this case, the transition from left to right or from right to left is taken. And third, so the search is at an edge of the sector exactly when an object is detected. So in this case, an arbitrary transition is taken, that is, the robot might approach the object or it might change the direction of the search. So the non-deterministic behavior of the third case might cause the robot to fail to approach the object when it is first detected. So if this event occurs at the same time at the event of reaching positive or negative 45 degrees, however, after a short period of conditions will be checked again and it is likely that only one of the events will occur. So the last topic is the implementation of finite state machines. So this is an example of a algorithm of the persistent uh, persistent Breitenberg vehicle, which is first discussed earlier. So from FSM, we can convert it into algorithm just like this. So we need variables uh, to declare these data. So a timer variable that is set to a desired period of time. So in milliseconds and states, the current state is in forward. So the initial state is forward, so you set the left and right motor to 100. So it will move forward and then loop. So when current state is equal to forward, so which is now forward state, and an object is detected in front, so you set the left and right motor power to negative 100, meaning it will reverse, it will move backwards. And then the timer set to 1000, so that is 1 second, and you change the current state to back. And when the current state is equivalent to back and the timer is 0, so again, you will set the left and right motor to 100 and the current state to. So finally, the summary. So most robotics algorithms require that the robot maintain an internal representation of its current state. So conditions that the robot uses to decide when to change state and actions taken when changing from one state to another are described by FSM. So FSM are used to understand uh, the movements of a robot rather than you turn on the robot and you observe what will be its movement. So it's easier to understand a robot using FSM. So state variables are used to implement state machines in programs. So uh, from those FSM, so you can create algorithms. So and those algorithms are the ones you're gonna use to program the robot use. And that's all, and I hope you learned something.